And next up, the transaction graph for modeling blockchain semantics with Pedro Moreno-Sanchez. He'll be videoing in.
Yep. Hello, everybody. Thank you for the introduction, and apologies for not being able to be there. I couldn't travel due to the restrictions of the coronavirus. Yeah, my name is Pedro Moreno-Sanchez, and today I'm going to talk about the transaction graph for modeling blockchain semantics. Most likely, it's not a surprise for you that the success of Bitcoin from 2009 has sparked the development of many other blockchains and other systems. For example, we have systems like permissionless smart contracts in Ethereum, consortium blockchains like Hyperledger Fabric, and we also have several academic works that look at the different aspects of blockchains. For example, consensus protocols, what privacy guarantees are achieved or not, and many, many other aspects. However, each of these blockchains have its own set of operations, its own set of semantics, and the works that we have seen so far are targeted to one blockchain at a time and separately. So the goal that we are trying to do in this project is to find a unified way, a unified formal model that allow us to reason about properties of all blockchains at one time. And this is the main contribution of this work. So we defined a transaction-directed acyclic graph, which is a formal model that allows us to reason about the semantics of the transactions in blockchains. And we see that transactions are really the main core that appears in every blockchain that we have today. As I mentioned, this is a common framework that allow us to reason about the crucial properties across blockchains. As we will see, we can use TDAG to reason about conflict-free transactions, what is the validity of the blockchain state, what does it mean that the blockchain state is consistent, or what are the properties when we do composition of a state. Let me first tell you how our model, our TDAG, looks like. So our TDAG is a directed acyclic graph composed by a set of vertices and edges, and the vertices are divided in two subsets. The first one is called states, and we define them by this big circle. And they represent an atomic state in the blockchain. For example, modeling individual assets or coins in Bitcoin, or a variable in a smart contract, and so on. And inside these states, we define a special one, which we call the genesis state. And this represents the initial states that we have in every blockchain. The other type of vertices that we have are called witnesses, and we represent that by a square. And these model the data that we have to include in a transaction in order to verify whether the transaction is valid according to the rules encoded in the blockchain. And obviously, in every transaction in the TDAG contains only one witness. And we will see later why this is important. The set of edges are also divided in several subsets. One of them, we call them consignment edges, and they go from states to witnesses. And they model the fact that states are consumed by a transaction that contains the corresponding witness. And by consuming a state, I mean that transactions are updating states from one state to the other. For example, a transaction in Bitcoin are updating the ownership of coins from one public key to another one. The second set of edges that we have are observing edges. And this models the fact that a state can enter as an input of a transaction, but it still remains available to be consumed or to be updated by other transactions. And therefore, state can be observed by as many transactions as we need. And intuitively, this is the way that we have in our model to model the read operation. Finally, we have the producing edges that goes from witnesses to states. And these are the way that we have to model that a state is created by the transaction corresponding to the witness. Once we have defined vertices and edges, the other main part of our model are transactions. And a transaction is modeled as a weakly connected DAG that has a set of input states, a set of output states, and a single witness. And these have to fulfill a set of requirements. In particular, every input state in a transaction must be a source, meaning that it has only outgoing edges. Every output state must be a sink, meaning that it has only incoming edges. And the set of vertices are composed by all the states and the witness itself. And on the side of the edges, we make two restrictions. So a consuming edge or an observing edge must connect an input state to the witness, and a producing edge must link the witness to an output state. Let me show you how this restriction makes sense in practice. In particular, we define several transaction types, that's defined in this slide. The first one, the init, represents what we call the genesis. For example, in a system like Bitcoin, this will represent the creation of coins at the beginning of the system. We also have a transaction with a single input and a single output. And this allows us to model that a user, for example, Alice, pays to Bob the exact amount of coins, so transfer the ownership of coins from Alice to Bob. We also have single input and multiple output transactions, where Alice can pay to Bob, but maybe Alice has more coins than the one. We also have multiple input and single output, and this in practice may represent, for example, that Alice might require to put together several addresses to collect enough coins to pay to Bob. And finally, we also can model multiple input and multiple output transactions, which are similar to the previous case, but Alice not only pay to Bob, but also may receive some money back from the payment itself as the change address. So let me recap this model with an example of execution in Bitcoin. So we can have one transaction, denoted here by T0, where the Bitcoin blockchain is created, and all the coins are represented in a state here named S0. And this is a design decision that we do in our model to have an initial state, in this case S0, that has all the assets or all the coins, such that we can later argue about them in the rest of the model. For example, we can now argue about a second transaction that spend S0 in a certain manner. In particular, we can model a block reward or the creation of a new block, such that some coins from the initial pool S0 goes to the miner, here represented as S2, and the rest of the coins goes to another state S1, such that we can reason about them later. And here, the vertex W1 represents the witness of the transaction, which in this case will be the proof of work that the miner has to show in order to create a valid block. We can, as you mentioned, we can further reason about this execution in Bitcoin. For example, we can also model a transaction where the miner uses the coins that he got in S2 and transfers some of them to another user V in S3. And we can also model that such a transaction can have a fee that is then defined in S4. And here, as you may imagine, the witness part represents the signature that the sender, in this case the miner, has to create in order to perform the transaction. I have given you only the details of an execution in Bitcoin, but in the paper we have more details of how to use our model for not only coin transfer blockchains like Bitcoin, but also smart contracts like Ethereum and consortium blockchains like Hyperledger Fabric. In the second part of the talk, let me show you how we can use this model to reason about properties in blockchain. The first one that we're interested in is called, or we call it, conflict-free transactions. And the idea is that a conflict in a cryptocurrency is common and occurs when there is an attempt to have a double spend, meaning that a single state is trying to be spent twice. In the sense, like I have some coins and I try to pay Bob and Caro at the same time with the same coins. Double spending in our model in TDAG will require that a single state has two different consuming edges. You should remember the notion of transaction that we have seen before. This is not allowed by definition of transaction itself. Therefore, so our TDAG must not have any double spending. However, the challenge comes when we have a TDAG, which is valid, and we have other transactions. So how we can add those new transactions into the TDAG itself, such that by adding these new transactions, we are not adding conflict, or we are not adding the double spending. So for that, we define formally what conflict freedom means. Consider a deck that has some states, some witnesses, and a set of edges that are divided in producing and consuming edges. And every transaction contains a witness W. So we say that such a DAG, such a tree, has no conflicts if every state has at most one producing edge and one consuming edge. And this definition can be used in practice, for example, by a miner that has a mempool of transactions and can check locally whether these transactions are conflict free, or in other words, if those transactions don't represent a double spending on its own. Once we have that, the next natural step is how we can add those conflict-free transactions to a TDAG. And for that, we show how to do such an addition, and we show in the paper that when we have a conflict-free set of transactions and we add it to a TDAG, if we follow the procedure in the paper, the resulting graph that we get is also a TDAG. So intuitively, if this theorem shows that or proves that following the addition mechanism that we have, the result is also a TDAG, meaning that we can safely add transactions to the blockchain. Finally, we are also interested on composition. And we are interested in that because in practice it shows in several applications. Imagine, for example, that a miner may handle more than one blockchain at a time. There are settings like sharding, where miners are handling several copies of the blockchain, or we have transactions that require information from several blockchains at a time, which is called interchain transactions. We have studied that. We have given a way of composing several TDAGs and showed that if we compose two TDAGs, G and G prime, the result is also a graph, G tilde, such that it's also a TDAG itself. In other words, so we show how you can compose two TDAGs and in a safe manner, such that you have the result as another TDAG for which you can still reason again with the properties that we have seen so far. To conclude this talk, we have seen how blockchains are great of interest for financial industry and also academia. However, we are lacking formal models that allow us to reason about them in a unified manner. In this work, we have proposed TDAG, a formal model that allows us to reason about the semantics and properties of blockchains. And we include interesting properties such as conflict-free of transactions, or how we can compose TDAGs, or how we can compose blockchains. And the most interesting insight, perhaps the most interesting insight, is that it allows us for the first time to reason about different blockchains, Bitcoin, Ethereum, or Fabric, within a single model, abstracting away the peculiarities of each of them. This model obviously is the first part of our work, and in the future we would like to extend it to add to encode more applications such as off-chain transaction, payment channels, or commit chains, and many other technologies that are coming today. With that, I would like to thank you for your attention and answer any questions that you might have. Thank you very much.
Do we have any questions from the audience? I see one coming down.
Hi, very cool work. I'm just wondering if you guys have considered including into the formalization more specific aspects of blockchain design, like the cryptographic primitives that are used, or the incentive mechanisms that are used. Have you considered extending that, or how could your model eventually use to reason about that in a more formal way?
This is a really interesting point. So far we have considered only a static execution of the blockchain, meaning that you give me a current setting of the blockchain and we can model it with our model. So we don't have these dynamic properties that incentives or how the different cryptographic assumptions might gather together. But definitely an interesting follow-up of the work, how to add all those dynamic properties inside the model. Yes.
Oh, hi. I was assuming this is detailed in the paper, but I was wondering what kind of challenges you encountered when reconciling account-based and UTXO-based models.
So the main challenge there was how we model all the possible states at the beginning. So as I mentioned, there is this init transaction where we have to have an initial state that defines all possible states that might appear later in the execution. And this is one of the reasons why we are considering static executions from the model. So in account-based, we have had to have one state per account, but then add some kind of timestamp or sequence number so we can differentiate every state for the account at each point of time. That was the main challenge. We needed to add some kind of differentiation in terms of timestamp or sequence number that allow us to differentiate the state of the account at each point in the execution. And this doesn't happen, for example, in UTXO because every state is used only once. So naturally, once it's consumed, we don't have to reason about it anymore. But this is not the case in account-based, indeed.
Hi, Brendan Marr here. Question, this is regarding combining chains.
Mm-hmm.
So are you implying that if you have two chains that are independently Turing complete, that if you combine them, they can become Turing incomplete? Or am I totally off base?
I couldn't hear the question correctly, sorry. Can you repeat it?
Are you saying that if you can combine two chains that are Turing complete, that they can combine into one chain which is Turing incomplete?
I don't think so. So what I'm saying, or what we do in this paper, is that if we have two executions, for independently of whether they are Turing complete or not, but we have two snapshots of two blockchains, and we can prove that both of them separately are two TDAGs, we can combine them, and they will still be valid TDAG according to our model. But in the sense, and this is independent whether they are Turing complete or not. So what we need is a snapshot of them. And once you have a snapshot, you have all the operations that have been done so far from the beginning until the moment that you have the snapshot.
Okay, thank you.
All right, that's all the questions. Thank you again, Pedro, for giving your talk.
Thank you.